Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
You know, when we usually try to picture cosmological timeframes or just massive structures in space, there is this built-in assumption of, relative serenity. Like we look up and the visual data we get implies this slow, sweeping choreography.
Right, the rotation of galactic disks or the quiet gravitational dance of local groups, it all feels very distant and, frankly, mathematically stable.
Exactly. It feels stable. But the thing is, we're looking at a freeze frame.
Yeah, that perception of stability is really just a byproduct of our extremely narrow temporal window. I mean, human observation represents less than a fraction of a millisecond on the cosmological clock. We are literally just getting a snapshot.
Which is what makes it profoundly jarring when we point our instruments at a specific coordinate. In this case, we're talking about right ascension 0, 6 hours, 58 minutes, declination minus 55 degrees. And we realize we aren't looking at a stable gravitational system at all.
No, not even close.
We're looking at a multi-megaparsec crime scene, just a catastrophic kinetic event of absolutely unimaginable proportions.
It really is the pinnacle of astrophysical violence. We are analyzing the immediate aftermath of a colossal merger between two distinct galaxy clusters. And this specific shock front, which is still traveling through the intergalactic medium, was generated roughly 4 billion years ago.
4 billion years. Just want to anchor that for you listening. As the photons and X-ray emissions from this event were just beginning their transit toward our sector of the Milky Way, the Earth was in its Hadean to early Archean eon.
The very beginning.
Right. The absolute earliest precursors to single-celled life were just barely beginning to synthesize in these primordial oceans. Meanwhile, across the observable universe, billions of solar masses were being subjected to extreme ram pressure stripping.
It's a staggering timescale.
And we are only just now processing the telemetry from that wreckage. But the reason we are analyzing this today isn't just a gawk at a fascinating kinetic anomaly in space. This specific region, cataloged as 1E065756, but universally known as the Bullet Cluster.
The famous Bullet Cluster, yes.
Right. It has served as the ultimate empirical battleground for modern physics. It is essentially the primary proving ground for the dominant cosmological paradigm, which is the existence of dark matter.
Yeah, for over 2 decades now, the Bullet Cluster has basically operated as the cornerstone of the Standard Model. It was essentially treated as the incontrovertible empirical proof that cold, collisionless dark matter isn't merely a mathematical placeholder.
It's a physical reality.
Exactly, a physical reality. It formed the absolute bedrock of our understanding regarding the universe's unseen mass budget.
Okay, let's unpack this. Because our mission today is to completely reevaluate that bedrock. We are analyzing how a suite of radically precise multi-wavelength observations of this exact celestial structure are currently threatening to upend the entire dark matter consensus.
It's a major paradigm shift.
We are looking at new spectroscopic data that essentially takes a sledgehammer to the standard interpretation of the Bullet Cluster. And it potentially revives a 4-decade-old theoretical framework that the mainstream physics community honestly largely abandoned a long time ago.
The current developments surrounding the Bullet Cluster really offer a masterclass in how scientific epistemologies must adapt when our instrumental resolution increases. I mean, the physics community operates under heavily scrutinized paradigms, but the universe is not obligated to conform to our preferred model.
No, it definitely isn't.
Right, so when observational capabilities cross a new threshold, like in this case, unlocking unprecedented spectroscopic clarity, the foundational pillars of our standard models are subjected to extreme stress testing.
Yeah, and that stress test is happening right now. Let's set up the parameters of the initial collision before we get into the new data, just so everyone is on the same page. We are talking about 2 distinct galaxy clusters.
And these are not small structures.
Right. For those of you deeply immersed in this field, you already know we aren't talking about small, localized groups of stars. These are massive, gravitationally bound structures positioned at a redshift of roughly z equals 0.296.
The scale is absolutely vital to keep in mind here. We are dealing with a main cluster and a slightly smaller subcluster. Combined, we are analyzing a system that contains thousands of individual galaxies.
Thousands of galaxies, not just stars.
Yes, entire galaxies, all bound within an extensive gravitational potential well. But the kinetic variables are what make this merger so unique. The subcluster, which we call the bullet, was on a highly centralized trajectory.
Like a direct hit.
A completely direct hit. It passed directly through the core of the main cluster at extraordinarily high relative velocity. We are observing a shock velocity approaching 4,500 kilometers per second.
Wow.
And the subcluster itself is moving at roughly 2,500 kilometers per second.
Let's just hold on that relative velocity metric for a second, because that is wild. 2,500 kilometers per second. That translates to a Mach number of roughly 3 within the context of the surrounding intergalactic medium.
Which is incredibly fast for an object of that mass.
Right. The kinetic energy dissipation required to halt, or even just slow down an object of that size moving at Mach 3 is completely staggering.
The energy released in this event is literally second only to the Big Bang itself. I mean, it is a thermodynamic extreme. But to model the mechanics of the collision accurately, we have to look really closely at the mass distribution of the clusters themselves.
Okay, break that down for us.
Well, as we know, the visible galaxies, the stellar populations that we see shining, account for a surprisingly small fraction of a cluster's total baryonic mass. I mean, the ordinary matter, the vast majority of the ordinary matter resides in the intracluster medium, or the ICM.
Right, the ICM. That's the hot, diffuse plasma that fills the empty space between the constituent galaxies.
Mm-hmm.
It's so easy to look at optical imagery, like from Hubble, and just assume the stars are the primary actors in these structures.
Exactly, because that's where the visible light is.
But chemically and physically, the stars are really just trace elements floating inside a massive reservoir of ionized hydrogen and helium, right?
Right. Yes, the mass ratio is heavily skewed. The hot plasma of the ICM actually outweighs the combined stellar mass of all the galaxies within the cluster by a factor of anywhere from 5 to 10.
5 to 10 times more mass in the gas than in the stars.
Right. So when we analyze the kinetic mechanics of this high-speed merger, the primary physical interaction isn't between the stars at all. It's the collision of these two massive plasma clouds.
Which introduces fluid dynamics into the equation. We have two colossal volumes of intercluster medium hurtling toward each other. And because plasma is a collisional fluid, the moment those two volumes intersect, the physics get incredibly violent.
They do. They don't just slip past one another like ghost ships.
Right. They experience extreme ram pressure. Like as the subcluster's gas plows into the main cluster's gas, the collisional cross-section of the protons and electrons is incredibly high.
They essentially slam into a wall of their own making. The gas clouds subject each other to immense drag forces, and they rapidly decelerate. All that kinetic energy from the 2,500 kilometer per second impact is violently converted into thermal energy.
Heating the plasma up to insane temperatures.
Yes, heating it to the point where it becomes a massive source of Bremsstrahlung, or what we call braking radiation.
Braking radiation, yeah.
Yes,
Let's
Joe.
touch on that, because it's super important for how we actually see this stuff.
Right, so the deceleration of those charged particles in the plasma generates intense X-ray emissions. When we map the bullet cluster today using the Chandra X-ray Observatory, what we are actually detecting is this superheated, shocked plasma.
It's glowing in X-rays.
Exactly. It presents as two distinct, incredibly bright lobes of gas that have been severely slowed down and basically trapped in the central region of the collision zone. And the morphology of the smaller gas cloud literally looks like a ballistic wake.
Like a bullet.
Like a bullet shape, yes, which is exactly what gives the cluster its name.
But here's the critical point of divergence in this whole event. While the intracluster medium was slamming into this hydrodynamic wall and bleeding off its kinetic energy in X-rays, the constituent galaxies themselves experienced an entirely different physical reality.
Completely different.
The actual stellar populations, all those billions of stars locked inside their respective galactic structures, basically ignored the collision entirely.
Yeah, they really did, because unlike the plasma of the ICM, the galaxies effectively behave as collisionless particles within the broader cluster environment.
Meaning they don't hit each other.
Right. The mean free path of a galaxy moving through another cluster is so massive compared to its actual physical cross-section that the probability of direct stellar interactions is statistically negligible.
It's the classic disparity between collisional and collisionless matter. I was trying to map this conceptually for you listening, and it essentially mirrors firing two blasts of birdshot at each other through a dense suspended water droplet.
That's a great analogy.
Thanks. So the lead pellets, which represent the galaxies in this case, have such a small cross-section relative to the vast distance between them that they just zip right past each other unhindered. They carry their momentum out the other side.
They don't even notice the other pellets.
Exactly. But the water, which represents the dense intracluster plasma, smacks together, splatters, and stalls out completely in the center.
The fluid dynamics versus n-body dynamics analogy holds up perfectly there. The galaxies retain their initial velocities while the gas is stripped away via ram pressure. The result is a profound physical separation of the cluster's components.
A total decoupling.
Right. So following the transit, you have the bulk of the baryonic mass, which is that X-ray emitting plasma, stalled right near the center of the gravitational potential. Meanwhile, the two groups of galaxies have sailed straight through and are now positioned on the far outer flanks, millions of light years away from their original gas halos.
We have a macro-scale centrifuge. The collision literally physically isolated the galaxies on the outer edges, leaving the heavily dominant plasma mass segregated in the center.
Yeah.
So we possess an incredibly clear, bifurcated map of the system's normal matter. So my question is, why did this specific segregation turn into the foundational proof for dark matter?
Well, the crux of the argument relies entirely on general relativity, specifically the mechanics of gravitational lensing. We know from Einstein that any localized concentration of energy or mass induces a curvature in the surrounding spacetime metric.
Right, it literally bends space. And photons, even though they are totally massless, are constrained to follow these curved geodesics. So a massive foreground object acts like a giant gravitational lens.
Exactly. It deflects the light emitted by background sources. When we examine the deep field optical data behind the bullet cluster, we observe a highly pronounced weak lensing effect.
The background galaxies look all warped.
Yes, they are subjected to shear forces, distorting their apparent morphologies into these faint little elliptical arcs. By statistically analyzing the orientation and the magnitude of these shear deformations, astrophysicists can mathematically reconstruct the exact distribution of the foreground mass that is causing the lensing.
So we can basically build a high-fidelity topographical map of the cluster's gravity.
A map of the gravitational potential, yes. So we have two distinct maps to compare. We have the X-ray map, which shows us exactly where the baryonic mass is.
That huge pool of hot gas stalled in the center.
Right. And then we have the lensing map, which shows us exactly where the gravity actually is. The expectation, if we base this on purely baryonic models of the universe, was that the deepest gravitational potential wells should perfectly overlap with the highest concentrations of mass.
Because more stuff equals more gravity.
Exactly. And since the X-ray data proves that the vast majority of the normal matter is stalled in the central plasma clouds, the gravitational lensing should be heavily centered over that plasma.
But it isn't. And that right there is the paradox that ignited the modern cosmological consensus. When you overlay the X-ray mass map with the gravitational lensing map, there is a massive, glaring spatial offset.
The huge offset.
The strongest gravitational lensing isn't happening over the massive gas clouds in the middle. The deepest gravity wells are sitting right on top of the separated galaxy groups on the outer flanks, where the stars ended up.
Yeah, the spatial offset between the baryonic mass peaks and the gravitational lensing peaks was measured at roughly 8 sigma. I mean, it is an undeniable, mathematically robust discrepancy. The system is generating immense localized gravity in regions where there is seemingly very little mass.
Wait, so the light is bending the most where there's seemingly the least amount of stuff? How is that physically possible unless our math is totally broken?
Well, if we rely strictly on the observable baryonic matter, the math is entirely broken. The light is being sheared the most by regions containing the least amount of material, unless, of course, we introduce a non-baryonic variable into the equation.
And here we go. This is where cold dark matter, or CDM, enters as the savior of the standard cosmological model.
It really was the savior. The lambda CDM framework posits that the universe is overwhelmingly dominated by a non-baryonic particulate substance that interacts exclusively via gravity,
while remaining completely decoupled from the electromagnetic force.
Exactly. It is entirely immune to the electromagnetic spectrum. It doesn't emit, reflect, or absorb photons in any way, making it fundamentally invisible. But more crucially for the bullet cluster scenario, its lack of electromagnetic interaction means it cannot experience friction or ram pressure.
Right. The collisionless nature of dark matter is its defining characteristic here. So prior to the merger, both the main cluster and the subcluster were modeled as residing within these massive extended dark matter halos.
And those halos contain the vast majority of the system's total mass.
So let's run the n-body simulations again, but with the dark matter halos included this time. The clusters collide. The collisional plasma hits the wall. generates X-rays, and stalls out in the center. The collisionless galaxies sail right through. And the dark matter halos, what happens to them?
Well, they behave exactly like the collisionless galaxies. Because dark matter particles cannot interact with the gas, or even with each other, they experience absolutely zero hydrodynamic drag. The dark matter halos simply pass right through each other, remaining gravitationally bound to the collisionless stellar populations.
They segregated themselves completely from the plasma.
Yes.
So the reason the gravitational lensing is occurring so intensely on the outer flanks is because the invisible dark matter halos are sitting right there. They're heavily concentrated around the galaxies.
Exactly. They carried the vast majority of the mass outward, leaving the smaller fraction of visible plasma stranded in the center.
It was viewed as the ultimate elegant triumph of the lambda CDM model. The bullet cluster essentially provided a macro-scale particle accelerator, naturally separating the collisional baryonic matter from the collisionless dark matter.
It was textbook. The spatial offset between the X-ray peaks and the lensing peaks was considered impossible to explain using any modified theory of gravity because you were clearly seeing the source of the gravity physically separate itself from the normal matter.
But I'm going to push back on this elegance a little bit.
Yeah.
Because from an epistemological standpoint, introducing a completely unobservable substance to fix a gaping hole in your gravitational math carries a distinct scent of, well, ad hoc reasoning.
It's a common critique, yes.
It feels uncomfortably close to adding epicycles to the geocentric model. Yeah. So let me get this straight. We saw gravity where there was no visible mass. And instead of rigorously questioning whether our fundamental laws of gravitation, whether Poisson's equation or general relativity break down at extreme low acceleration scales, we just assumed there was a giant, invisible, frictionless ghost substance perfectly placed exactly where we needed it to be.
This raises an important question, and honestly, that critique is the very engine of alternative cosmological theories. You are completely right to be skeptical. The lambda CDM model requires us to accept that 85% of the universe's mass is fundamentally beyond the reach of the standard model of particle physics.
85%, that's almost everything.
Right, and despite decades of direct detection experiments, looking for weakly interacting massive particles or WIMPs using highly sensitive underground xenon detectors, we have found absolutely nothing. Not a single particle. So the reliance on dark matter is heavily predicated on its macroscopic gravitational effects, not on direct particle verification.
And that reliance remained relatively unshaken. The bullet cluster was treated as the closed case until very recently, because the fundamental weakness of any empirical model is that it is only as robust as the instruments used to compile the data.
And our instruments just got a massive upgrade.
Exactly. The data landscape has radically shifted with the deployment of the James Webb Space Telescope.
The leap from legacy observatories like Hubble or Chandra to the JWST is fundamentally a leap in spectroscopic resolution. The original bullet cluster analyses were primarily relying on optical lensing data and X-ray mass derivations.
Which were great for their time.
They were. And while they were accurate within their design parameters, they completely lacked the extreme infrared sensitivity required to depthly analyze the chemical composition of the stellar populations locked inside those outer galaxy flanks.
Right. And a recent analysis led by an international team, including Professor Pavel Krupa and researcher Dong Zhang from the University of Bonn, leveraged this new capability. They utilized the JWST's near-infrared spectrograph and mid-infrared instrument to conduct an unprecedented chemical assay of the constituent galaxies in the bullet cluster.
They weren't just counting the light sources anymore.
No, they were measuring the specific absorption lines in the stellar spectra.
Because spectroscopy allows us to determine the exact elemental abundances within those remote galaxies. Different elements absorb light at highly specific wavelengths, creating unique chemical fingerprints.
It's like a barcode for the universe.
Exactly. And the critical revelation from Krupa and Zhang's analysis was the detection of exceptionally high metallicities. Specifically, they found profound concentrations of heavy elements like oxygen, magnesium, and notably iron.
And just to clarify, within the context of astrophysics, metals refers to any element heavier than helium, right?
Yes. Astronomers are lazy with chemistry. Anything heavier than helium is a metal.
Right. So the presence of these heavy elements in such high concentrations is the loose thread that begins to unravel the standard dark matter narrative for this cluster, because these elements cannot be synthesized in the primordial universe.
No, primordial nucleosynthesis following the Big Bang only yielded hydrogen, helium, and very trace amounts of lithium. The entire heavy element inventory of the universe must be forged within the cores of stars via ongoing stellar nucleosynthesis.
A star is functionally just a hydrostatic balancing act. You have immense gravitational pressure crushing inward, and that's balanced by the outward radiation pressure generated by the continuous nuclear fusion of hydrogen into helium.
But the fusion chain doesn't stop at helium, provided the star has sufficient initial mass. To synthesize oxygen and iron, you require the extreme temperatures and core pressures found only in the most massive stellar classifications. We're talking about stars exceeding 8 to 10 solar masses.
Massive stars. And this brings us to the initial mass function, or the IMF. For those listening, that IMF is basically the demographic distribution of a star-forming region. It tells us the ratio of small, low-mass stars to giant, high-mass stars when a galaxy forms.
Exactly. And generating the specific abundance of iron that was observed by the JWST in the Bullet Cluster necessitates a highly specific stellar history, because iron is the terminal point of stellar nucleosynthesis.
You can't fuse iron and get energy out of it.
Right. The fusion of iron is an endothermic process. It drains energy from the core rather than releasing it. So when a massive star develops a critical iron core, the outward radiation pressure collapses almost instantaneously.
Gravity wins the battle in a fraction of a second.
Yes. The stellar envelope implodes at a significant fraction of the speed of light, rebounds off the incompressible core, and detonates in a core collapse supernova. That violent explosion is what seeds the surrounding intergalactic medium with all the iron and oxygen the star spent its entire life forging.
So when Krupa and Zhang's team measured this intense iron enrichment in the Bullet Cluster's galaxies, they had to work the nucleosynthetic math backwards. They determined that the stellar initial mass function for these galaxies must have been extremely top-heavy in their past.
Extremely.
To produce that much iron, a staggering number of extremely massive stars had to have been born, rapidly exhausted their fuel, and detonated.
That the galaxies are fundamentally older and have cycled through far more massive stars than previous models ever accounted for. But the supernova doesn't eradicate the mass, right? It just redistributes it. The outer envelope is blown away, but the collapsed core of the progenitor star remains.
Here's where it gets really interesting. This is the critical recalculation of the baryonic mass budget. Depending on the exact mass of the progenitor star, the core collapses into either a neutron star or a stellar mass black hole.
These are our stellar remnants.
Right. And they possess immense mass, often several times the mass of our sun, but their physical volume is infinitesimal, and they emit essentially zero luminosity in the optical or infrared spectrum.
They are dark baryons. They are structurally invisible to our telescopes, but they contribute massively to the gravitational potential of the galaxy. So the Bullet Cluster flanks are essentially heavily populated graveyards.
Just absolutely littered with millions of these non-luminous, ultra-dense stellar corpses.
And the implication for the dark matter debate here is just profound. When earlier cosmologists analyzed the Bullet Cluster, they calculated the visible stellar mass using standard mass-to-light ratios. They looked at the luminosity, estimated the mass of the living stars, and concluded it wasn't nearly enough to explain the gravitational lensing peaks.
Therefore, they filled the mathematical void with non-baryonic dark matter.
Exactly. But the JWST data fundamentally alters that mass-to-light ratio. It proves that the living luminous stars are just the tip of the baryonic iceberg. There is a massive, highly concentrated population of dark baryons, these dead stellar remnants, hiding right alongside the visible galaxies.
We assumed the missing mass was an exotic, collisionless ghost particle, but a huge percentage of it is actually just incredibly dense, perfectly normal matter that simply burned out billions of years ago.
Right. Co-author Dr. Indranil Benik from the University of Portsmouth led the mathematical integration of this newly discovered mass. By calculating the total mass of the requisite progenitor stars needed to produce the observed iron yields, and then factoring in the mass of the resulting neutron stars and black holes, Benik demonstrated something huge.
What did he find?
He showed that the total baryonic mass residing in the outer flanks of the Bullet Cluster is vastly higher than historically assumed.
Okay, but we have to be really precise here. Does adding all of these stellar remnants, all these dark baryons, completely bridge the math gap? Like, if we stick to standard Newtonian dynamics and general relativity, is this new mass enough to explain the extreme weak lensing shear on its own without any dark matter at all?
Within the strict confines of the lambda CDM model and general relativity, no, it isn't. The newly quantified mass of the stellar remnants is substantial, yes, but it still falls short of fully explaining the absolute magnitude of the gravitational lensing peaks. There is still a missing mass problem if you adhere to Einsteinian gravity.
Okay, so the standard model survives. Dark matter is still required, just, I guess, slightly less of it.
Well, that assumes we refuse to question the laws of gravity themselves. The true disruption caused by this study occurs when you apply this newly corrected baryonic mass distribution to the primary alternative cosmological model.
Which is MOND.
Yes, MOND.
Modified Newtonian dynamics. This is where the physics gets deeply controversial. MOND has essentially been the perennial underdog of theoretical physics since it was first formulated by Mordechai Milgram back in 1983.
Yeah, Milgram recognized the missing mass problem in the flat rotation curves of spiral galaxies. Newtonian dynamics dictates that the rotational velocity of stars at the extreme edges of a galaxy should drop off squarely as a function of their distance from the central mass.
Just like planets in our solar system, the further out you go, the slower they orbit.
Right, but observational data universally shows the velocity curves plateauing. The outer stars move far too fast, implying a massive halo of unseen matter holding them in.
But Milgram's approach to fixing this was radically different. Instead of injecting an invisible particle to increase the mass, he proposed modifying Poisson's equation for gravity itself. He suggested that gravity does not strictly adhere to the inverse square law at extremely low accelerations.
He introduced an acceleration constant called a naught, which sits at roughly 1.2 times 10 to the negative 10 meters per second squared. Above this threshold, gravity operates exactly as Newton and Einstein described.
So here on Earth, or in our solar system, Newton and Einstein work perfectly.
Perfectly. But below this threshold, in the deep, ultra-low acceleration regimes at the outer edges of galaxies, gravity transitions to a different dependency. It becomes linearly proportional to the mass, rather than decreasing by the square of the distance.
It's a phenomenological model, right? But its predictive power regarding galactic kinematics is kind of astonishing. Like the radial acceleration relation, which plots the observed acceleration against the expected baryonic acceleration, it follows the MOND prediction perfectly across hundreds of structurally diverse galaxies.
With zero need for dark matter tuning.
Right. Yet despite its success on galactic scales, MOND was heavily marginalized by the broader cosmological community. And the primary empirical weapon used to suppress MOD for the last 20 years has been the cluster scale dynamics, specifically the bullet cluster itself.
Because when earlier researchers applied the MOND framework to the old bullet cluster data, it failed. Spectacularly failed, yes. Even when applying MOND's modified gravity to the visible stellar mass in those separated galaxy flanks, the resulting gravitational potential simply wasn't deep enough to explain the observed lensing shear.
MOND could explain isolated spiral galaxies, but it seemingly broke down entirely when applied to colliding galaxy clusters. The mainstream consensus solidified right then and there. MOND was mathematically inadequate, and the bullet cluster proved that non-baryonic dark matter was unequivocally necessary.
But that historical failure of MOND was predicated on an incomplete baryonic census. They were running the MOND equations using only the mass of the luminous stars. They were completely blind to the massive reservoirs of dark baryons, the black holes in neutron stars that the JWST has now exposed via the iron abundance.
And this is the crux of Banach and Zhang's breakthrough. They returned to the MOND framework, but this time they integrated the newly verified baryonic mass budget. They took the visible stellar mass, added the immense mass of the dark stellar remnants inferred by the heavy element spectroscopy, and applied Milgram's low acceleration modifications to that combined total.
The recalculation of the century, honestly.
So how did the tensors resolve when they ran the math this time?
The fit is remarkably precise. When the dark baryons are accounted for, the MOND model flawlessly reproduces the exact spatial offset and the precise magnitude of the gravitational lensing peaks observed on the outer flanks of the bullet cluster.
Wow.
The missing mass problem in this specific collision system entirely evaporates.
Let me synthesize the magnitude of this, because it's huge. Wait, so are they saying dark matter is a total myth? The single greatest empirical pillar supporting the existence of dark matter? The exact celestial anomaly that the standard model used to effectively bury MOD 2 decades ago has just been entirely reverse engineered. The JWST essentially proves that the lensing can be fully explained by the gravity of dead stars operating under modified acceleration parameters.
Yeah.
No exotic collisionless ghost particles required at all.
Professor Krupa is unambiguous in his interpretation of these results. He argues that the lambda CDM requirement for non-baryonic dark matter in the bullet cluster is now scientifically obsolete. The dark baryons provide the requisite localized mass, and MOND provides the correct gravitational mechanics to explain the shear.
It is a completely self-consistent baryonic solution.
Exactly.
But, I can hear the immediate counter-arguments from the lambda CDM loyalists, because accepting MONE requires accepting a fundamental violation of the strong equivalence principle, and it deeply complicates our understanding of cosmological expansion and the cosmic microwave background. So what if a physicist simply refuses to abandon general relativity? How does this JWST data impact the standard model if we rigidly reject MOND?
Well, the data forces a severe calibration even within the strictest confines of lambda CDM. The heavy elements are an observational reality. The progenitor stars existed, and their high-mass remnants are currently occupying those galaxy flanks. Even if you completely reject MOND, even if you maintain that general relativity is absolute and dark matter is necessary to bridge the final gap in the lensing data, you have to drastically alter your dark matter to normal matter ratios.
Because the dead stars are doing a massive portion of the gravitational heavy lifting that we previously assigned entirely to the dark matter halos.
Exactly. If the dark baryons are generating a highly significant percentage of the observed lensing shear, the mathematical requirement for non-baryonic dark matter in those specific spatial coordinates absolutely plummets.
Right.
The previously calculated mass of the dark matter halos surrounding those subclusters must be aggressively slashed, potentially by half or even more, to avoid over-predicting the total gravity, because dead stars are doing 50% of the pulling.
It's an epistemological crisis for the standard model, either way. You either adopt a modified theory of gravity that seemingly removes the need for dark matter entirely in this system, or you retain your dark matter, but admit your previous measurements of it were wildly inaccurate because you failed to account for a massive graveyard of dead stars hiding in the optical blind spots.
This specific observational shift underscores the vulnerability of cosmological models that rely heavily on inferred parameters rather than direct detection. For decades, the bullet cluster's discrepancy was mathematically smoothed over by invoking a highly specific, unverified particle.
We just assumed it was there.
Right. The JWST data suggests that the discrepancy wasn't necessarily a manifestation of new particle physics at all. It was rather a profound failure to fully inventory the normal baryonic matter using the limited spectroscopic tools of the past.
Let's pull this complex web of kinematics and astrophysics together. We initiated this exploration by examining a high-velocity merger between two galaxy clusters at z equals 0.296. We broke down the fluid dynamics, how the vast collisional plasma of the intracluster medium slammed together.
It generated extreme ram pressure and stalled out in the center, emitting intensely in the X-ray spectrum.
We contrasted that with the n-body kinematics of the galaxies themselves, which, due to their vast mean free paths, behaved as collisionless entities. They bypassed the central plasma shock front completely and segregated themselves on the outer flanks.
And then we explored the spatial anomaly that defined modern cosmology. The weak gravitational lensing shear indicated that the deepest gravitational potential wells were anchored to the outer galaxy groups,
completely offset from the central plasma mass.
Right, and this offset birthed the dominance of the lambda CDM dark matter paradigm, which posited that collisionless dark matter halos traveled with the galaxies and provided the missing gravity.
But the introduction of high-resolution infrared spectroscopy via the James Webb Space Telescope shattered that neat consensus. The detection of extreme metallicities, specifically heavy iron yields, necessitated a profoundly top-heavy initial mass function in the cluster's history,
which mathematically demands the presence of a vast, unseen population of dark baryons, the black holes and neutron stars left behind by those ancient, massive supernovae.
And finally, we saw how integrating this newly discovered baryonic mass breathes new life into modified Newtonian dynamics. By applying Milgram's low acceleration threshold to the combined mass of the visible stars and the dark remnants, researchers like Bannock and Zhang have demonstrated that the bullet cluster's extreme lensing can be resolved without invoking a single particle of non-baryonic dark matter.
It represents a paradigm shift of the highest order. A single refined observation has completely inverted the interpretation of the universe's most famous kinetic anomaly.
It reveals a profound epistemological truth about the nature of our cosmological pursuits. The models we construct are inherently fragile. They're always entirely beholden to the resolution limits of the era in which they were theorized. I mean, the bullet cluster was treated as an absolute, settled empirical truth for nearly a quarter of a century.
Yeah, but the universe remains profoundly indifferent to our consensus. It simply waits for us to engineer a more sensitive lens, forcing us to constantly question how much of our structural physics is fundamentally real and how much is merely mathematical scaffolding built to obscure the blind spots in our data.
A vital reminder that the science of the cosmos is never truly settled. If the bullet cluster, the absolute gold standard for dark matter, can be completely re-explained by just counting regular dead stars more accurately, how many other settled scientific facts are just waiting for a slightly better telescope to be completely rewritten? Thank you for joining us as we navigated the intense physics and evolving paradigms of the bullet cluster. Keep looking up and keep questioning the consensus. We'll catch you on the next deep dive.